Alright, I think we're good to go. So welcome back. Hope people had a good weekend. Hopefully you got some time off. And so we're in week 8 now. So it's a 10-week term. We have 3 weeks left, which means we have a total of 6 class meetings, and then we're done. So the quarter is wrapping up quickly. So what I'd like to do today is catch up on a few things related to stacks and queues and trees, some of which we've already done in the Monday-Wednesday class. And since the Monday class didn't meet yesterday, we've got some extra time over them. So I'm going to talk about that, and then eventually start talking about dynamic programming, which will be the subject of your last programming assignment. But first, let's talk about any questions. Oh, I have an announcement to make also. In spring term, there's a new class, CSE222B, which is a machine learning class, and that's being offered in spring. Scott Koss is teaching that. He's taught it before. It's generally seems to be a class students really enjoy. Minimal amount of prerequisites for it, but certainly anybody in here should have the prerequisites. All right, so someone in class has taken it and says it's a fun class, so unsolicited testimonial. So if you're looking for, I think it's 2 credits, and it fits into your schedule, consider that.
I have a question about the stacks and queues that we're about to get into.
Okay, go for it.
So, I did some reading around on other VSTs and how they structured their deletes, and a lot of the time I saw that they were just severing off the tree, and any nodes below the one you cut are just going to get thrown out in the garbage. But I usually saw them doing something with a queue, and I wasn't quite sure what they were doing. Are we going to incorporate stacks and queues into our delete algorithm in any way?
We're not. I'm not sure how you would use a queue in a tree deletion. Yeah, go ahead.
I stayed up late last night to get the delete, and I finally got it.
Okay.
But I wound up making a second recursive function just to take what will be the new parent node, orphaned off nodes, and homologate them into a single tree, and then once I get that node back, I place it where the deleted node was. So, I don't know if that would be
interesting. So to get full credit for PA4, it's got to be the same algorithm we've been doing in class. If what you've described does the equivalent modification to a tree to delete a node, then that's fine. But run some tests. There's sample executables. Make a small database, run some tests, and compare what the tree looks like after the test code deletes versus yours. That's one way to see if it's going to be doing the same thing. But you got to make sure you test the edge cases.
The edge case I had that was the silly one was the very top of the tree, but I got it to work on a small data set too.
So ultimately, deleting the root is where all the action happens. Everything else is recursive. So that's good if that worked. Some of the edge cases are, where you have nothing to the left of the root, or you have somebody, a stick figure doing yoga maybe. So nothing to the left of the root, that's one case. Something to the left of the root with other stuff on it is sort of the general case. Something to the left of the root which only has stuff to the left of it, that's another edge case. So where this node doesn't have anything to the right. in both of these cases, the largest node, let's call it L, should go up to the root. In this case, if you're deleting the root of this tree and there's nothing to the left, if this is null, then the new root becomes, you know, whatever's right here. That's the one exception to the rule. The rule being move the largest node from the left subtree up to the root. And then the one exception is if there's no left subtree, just move the root down to the right child.
Seeing as how we're initializing the basically the root that we found, or the node that we found as the root recursively, there's only so many cases, right, that could happen. There's only like 3 different cases or so that could happen that you're not accounting for, right? Like, so for like you said, the left is null, and then everything is totally normal. It's in the middle of the tree, and there's tons of data around it.
Mm-hmm.
Or the other one here on the right, where there's nothing to the right of the node. That's pretty much all that can happen, right, for the most part.
I think that's it, yeah. Those are at least the only cases you need to worry about with the algorithm we've been doing.
Yeah. Well, that's why I sent you that email to just look at it and just make sure I wasn't missing a case, because I did a bunch of drawings and stuff, and like you said, as soon as I drew everything out, it made it a lot easier to look at it and go, oh, you know, this is easily implementation.
Okay, cool.
But, okay.
Yeah, no, the code you sent looked like it was doing the same thing we'd been talking about, so I think that was good.
I tried to do it multiple times, and then I realized, oh, I have to be careful to not lose sight of the parent, because it's not a doubly linked structure.
Mm-hmm.
So I found it much easier to break the function into 2 different recursives. One where, you know, when you find a node that you want to delete, you get a handoff. The node that's going to get orphaned, and the node that will be the new parent to my other recursive function that orders it accordingly. And then when the delete function gets that result back, it makes it, it puts it in the spot where the deleted node was.
Mm-hmm. That sounds good.
I'll be really interested to see if we talk about it today, and then there might be just a much simpler, more efficient way to do this, like with tree free, as I discovered.
I found that order was very, very important.
Order is definitely important, but using lots of temporary variables can absolve you of some of the responsibility for tracking order.
Well, I remember at the beginning of my function, I originally had all of my declarations for the struct, current, and previous, or for that stuff.
Mm-hmm.
And it was giving me a seg fault, because by the time I checked the first case, they didn't know what to do with any of that stuff, and it hadn't really messed around with it. Wasn't calling it, and so for whatever reason it seg faulted. So I found if I moved it down and didn't allocate it until I actually needed it, then it actually worked fluidly. But that was one of the problems I was having. GDB was big help for that.
Okay, yeah, that makes some sense too. So a while back, you mentioned 2 recursive functions. So you really only need 1 recursive function, right? Which is getting down to where you're deleting the root. Once you decide your goal is to delete the root of a tree, see if there's anything to the left. If there's not, just move the root down. So that's an edge case you can dispense with immediately. Otherwise, focus your attention on the left subtree, which you now know is not null, because, you know, if it was null, you would have already done something. So just focus on the left subtree, and the next case is there a right child to that tree's root? If the right child is null, then this is the largest node in the tree, and your delete algorithm is pretty simple. Simply make this thing's right child the root's right child. So whatever root is pointing to on the right, just have this node point to that on its right, which we know is null right now, and then return this as the new root. Free that from memory. The third case...
Now what was causing the seg fault was when I was doing that case right there,
Mm-hmm.
I was trying to initialize larger to the parent right, for parent larger right, it was saying can't access memory at 0.
Right, right.
And so that's where my snake fault was.
Mm-hmm. All right, and then the third case is the one with the most work, which is where the right child of this subtree's root is not null, and that's where you need to find the largest and, you know, parent of the largest. And that you can do with a while loop. That's like our one while loop in the whole assignment, I think, other than the main program. That's where you move down with, you know, a pair of current, previous, and so on until you get to a spot where there's nothing to the right. Current's the largest one, previous is the parent of the largest. And then once you're there, it's a matter of putting the pieces together. So parent largest right equals largest left, which does that. Largest left equals root left, which picks up that. Largest right equals root right, which picks up that. Free the root and then return that as the new root. So it is complicated. It's possible to be overcomplicating it, but if you write it, you know, exactly the way I described it, it's pretty involved. And it's if you get it perfectly right, you'll know it. It'll work. Everything will flow through. You'll see the changes made to the tree. It'll make sense. If you don't get everything just right, if you get one little thing just slightly wrong, the whole thing might just like throw up all over your screen. Or it might, you know, be like, okay, no problem, I deleted it, you know, and then like 10 minutes later, it throws up on your screen, right? So it's a tricky function in that even if you do something wrong, it won't necessarily tell you right away. 50 lines or so I could see. And remember, this is all, you know, the base case that you use when you don't want to recurse. The normal approach is if you're deleting something to the left of the root, call the delete function on the left subtree, and then set the root's left to whatever that function returns. If you're deleting something to the right of the root, same thing. Otherwise, then you get into all of this stuff. Let's see. I'm reading a long question in direct message. Not parent largest and largest. Left equals null. 2 not largest parent largest. Right equals null. 3 we can find parent largest and largest. I think that's it, yeah. Yeah, I think if I understand the wording on that, those are the 3 cases. But yeah, it's left of the root is null, is one case. Second case, left of the root is not null, and the 2 cases are determined by that subtree. So the second case is, you know, the subtree has nothing on the right. Third case is the subtree does have something on the right, and then you can find largest and parent largest. So yeah, 3 cases. Cool.
Could you run by me one more time why the very bottom, on the left side of the tree, your third case there, why does that largest node get to be the root immediately?
So let me do some numbers instead. Alright, there's a nice complex tree. And we want to, there's some stuff over here. We want to delete the 100. And so the algorithm we're using in all cases, as long as there's something on the left, is replace the root with the largest thing in the left subtree. So just look at this, what's the largest number in there? It's going to be the 70. And so if we make 70 the new root, what does that do? It preserves the fact that this is a binary search tree, because everything over here is going to be less than 70, since 70 is the biggest thing in this tree. So if we move 70 up to the root, everything to the left of the root is smaller than 70. And everything to the right is bigger than 100, which is bigger than 70, because 70 was to the left to begin with. So by picking the largest thing in this tree, making that the root, we preserve the binary search tree characteristic. The left-right, less than, greater than property.
I just realized mine's wrong.
Oh, okay.
The reparenting algorithm I had, let's say you got rid of the 40 there.
Mm-hmm.
Or even, sorry, let's pretend you got rid of the 100 there.
Okay.
What I would actually do is I would set the 40 to the child that is going to be orphaned, and the right node as the one that's going to be the new parent.
Okay.
And then I would just take that 40. Yeah, I don't think mine's working. I can't explain it all, but I don't think mine's working.
So the only thing from here that can become the root is the 70, unless you start doing a lot more rearrangement. I mean, if I make 60 the root, 70 is going to have to suddenly go on the right side of the root, and you're going to have to start finagling over here, because currently, you know, the right side might be completely full, and you'd have to find a place to squeeze that new subtree in.
So is there weird algorithms out there that like someone wants you to do it that way? Because it seems like the way we're doing it is like the best way to do it.
Oh, there's lots of ways to do this. There's edge cases that I don't want to write because somebody will do it and say, you wrote that in class. But you know, there's certainly edge cases where you could get away with fewer operations. But the other thing is, you know, since we're always moving something from the left tree up to the root and then deleting the root, our tree is going to get kind of lopsided, right? Our left side is going to get smaller and smaller and smaller, and we never really touch the right side. And so it's possible we're going to bias the tree to be lopsided one way. Whereas, you know, it might make more sense to alternate which side we delete from, or to look at the subtree with the highest, the biggest height, and if the left subtree is the tallest one, right, then we'll take the largest thing from the left, put it to the root. If the right subtree is the tallest one, we take the smallest thing from the right and put that in the root. And so we could do some sort of, you know, attempt to keep the thing more balanced, and
Well,
so on.
If you're worrying about balance, then that could definitely, if you're deleting all the lower stuff, then you just have this big right side.
Yeah.
Nothing on the left. Okay.
Yep.
I can see that being an issue.
And so this is probably not what you would do in a you know, commercial package, for example. But I need to have a nailed down algorithm so I can see if the code was implemented correctly, basically. So it's purely a concession to being able to assess.
Now, so is this something we'll go into more algorithms, or you know, stuff like that at university, where you're going to elaborate more on different things you can do to keep the balance, or is that something that you just kind of have to do on your own while you're out there working with it?
We're going to actually talk about balancing trees. We're going to talk about AVL trees, and we'll see how to actually correctly balance a tree as you add or delete to or from it.
Oh, okay, cool.
Yeah, and that'll be more efficient than just kind of trying to like choose which side to delete from. Because inevitably, if we delete and we don't do something extra, our tree's probably going to become unbalanced. So we'll go through AVL trees. We'll probably go through red-black trees, which is another version of balancing a tree. And that's a quirky one, but I like to talk about it because it's a totally different approach to trying to achieve something from what we do in most of our algorithms. So yeah, we'll play around with balance a bit. So yeah, this is definitely a tricky algorithm. It's definitely the trickiest piece of the whole thing. The whole assignment has a lot of bits and pieces, but once you get your brain wrapped around recursion, most of those pieces start to kind of fall into place. one after another. The deletion is a real kind of oddball, because it's just a lot of manipulation. But go through it in pieces, and that third case where we've got to move down, find the largest and parent largest, break it into pieces. I would not try to go too overboard with modularizing into functions, because, for example, once we have the root of this tree, we need to find the largest and the parent of the largest. Well, if we just needed to find one thing, we could just return it as a function value. But since we need to find two things, and returning two values from a C function is tricky, right? We need to pass references to those, and so we're going to get into double pointers and things like that. It's easier to just code it in place. And it's the one function that you're kind of officially sanctioned to have a bunch of stuff in there that logically might be 2 or 3 separate tasks. But just iterate down like you do in your linked list, and find your largest, your parent of your largest, and maybe call this orphan, and then put the pieces together. This is root. And so it's parent largest right equals orphan, largest left equals root left, largest right equals root right, my free on the root, which not only frees the memory for the node, but also the strings that were allocated in there, and then return the new root, which is that largest node.
Yeah, when I did the freeze, I had to free everything individually. It was giving me memory leaks.
Mm-hmm. Yeah, you got to free the plate, first name, last name, then you got to free the struct node itself.
Oh, I thought you were saying that one function should clear all that stuff.
Yeah, you can make a myFree that clears all 4 of those things.
Oh, I guess so.
And then you just think of it like, oh, I just want to free this thing from memory, just call myFree. And then if you try to draw the arrows, right, this is picking up this is picking up this, and this is picking up this. Right, so your tree structure is getting all convoluted in memory, but that's okay, right? It doesn't have to look like a picture. I gotta close these shades.
Yeah, I think if it helps anybody else, I went through GDB and worked through that and really just kind of returned values as I worked through the function, and kind of saw how the recursion was working, and that obviously the node I was looking for was now the root and all this stuff. It checked the left, checked the right, and then I started drawing pictures, and that was like the hardest part. After that, the coding part was quick, because you realize how things are working and how you have to set it up.
Another great thing, I don't know how exactly to do it in GDB terminal, but something also really nice is like a debugger with a stack view. So you can see exactly what this callback is.
Mm-hmm. Yeah, and if you Google around a bit, you can find all kinds of initialization files for GDB that will do things like set up a view where you can see the stack on the side, and that can help if you're trying to sort of track and unwind the recursion in your head. Being able to see what's actually going on to the stack can help. But it can also get really complicated, because when you call a function, you don't just save the return address, you also save the local variables effectively. And so it can be tricky sometimes to know where you are, but there's tools that'll help you do that. Or, do it on a PIC processor, because it's a much simpler structure. And that would get you into some weird stuff. You have a bill with
NP Lab
addresses?
cool. Fantastic.
Oh,
Where to go?
yeah, somewhere.
Okay.
Maybe not.
Yeah, it was nice to see all the values at certain points.
Yeah, MP Lab is a pretty amazing debugger. It lets you do things visually. And with MP Lab, if you haven't taken 270 yet, cover your ears. With MP Lab, you can download a C compiler and compile C code into assembly language, and then run that through the debugger, and that can help sort of give you a view of what's going on when you call a function, and so on and so forth.
Yeah, that'd be nice to see what your variables are spitting out without having to individually print each one every step, you know?
Mm-hmm. Totally. We do that in 270 at one point towards the end, but you know, obviously we don't want people writing their assembly language code in C. But I was joking about cover your ears.
Yeah, we never did that with the we just strictly did our assembly language.
Yeah, it depends on how much time. There's a chapter in the book that talks about how for loops and if statements get converted into assembly language. But if there's time, and summer's usually a little tight, but it's fun to actually compile some stuff, and I've been doing that for my own stuff lately, so I'm definitely going to try to do that this summer. And
I've noticed a lot of compilers actually have flags for that kind of stuff. Like if you want to unroll for loops to optimizations, that's a flag I think you can give to GCC. And I know it's one you can give to the .NET Sharp one.
Yeah. If you look at the man page for GCC, I mean, it goes on and on and on and on and on, and it's just the options, right? It's just the dash things that you can specify, because you know, this thing has been developed over decades, and there's just so many things that you can do to customize it. So yeah, unrolling for loops is a nice way to improve speed, and you know, optimizations, turning off optimizations if you're trying to do some debugging, and you can put on bounds checking so that if an array goes out of bounds, it'll actually flag it, and so on and so forth. And it's fun to see how that maps into assembly language. All right. Other questions on PA4? If you don't actually end up putting the actual largest up to the root, you'll end up with a non-binary search tree, which means if you print your tree using in order, left node right, your data will come out unsorted, and that's the easiest way to see that something got moved that shouldn't have gotten moved to the root.
I just confirmed that it isn't working. I have a nice little test data set here where I have like the letters A, B, C, D, E, F, G, H, I.
Cool.
Because those are, you know, you know the alphabet, you can put those into a little tree. And C would be at the root of my tree initially, and then B and D would be its two children.
Okay.
And after I try to delete C, D becomes the new root.
Oh.
And I sort B somewhere into D's subtree.
Oh,
which
okay.
is not what we're looking for here. But, I think I can fix it.
Okay. Cool. Nice discovery then.
Yeah, I noticed on the last one that we chose, the root's always the last one. So I can't remember if it was, is it LRN, I believe? So that was a good way to test the edge case of deleting the root.
Right.
I did the sample program next to it and deleted it like 10 times to make sure that yours and mine all matched up.
Oh, cool. Yeah, so if you do left-right node traversal, the root of the entire tree is the last thing that comes out. So yeah, that's a really good test you just described. Keep deleting the root, and when you do this, you should be able to see what the root of the tree is, because it'll be the last thing printed in that post-order traversal, and so you can see if the correct thing got moved up to the root each time. That's a nice debug.
Yeah, and the other thing was I did the balance test that you described the other day,
Mm-hmm.
and I remember you said ants, bat, cat, but I put it in that order specifically.
Okay.
And it didn't balance the tree.
Right.
It added A first.
Yeah, right.
Am I doing wrong? So I actually went back and watched the video and wrote out what the tree's supposed to look like. Oh, that's what I did wrong.
Okay, cool.
It did say yes. So.
Awesome.
Just in case anyone's doing the test.
Yeah, yeah.
Do it in a certain order.
That's fantastic. These are like really good experiences to be having, right? I mean, if you could write the thing and it would work great the first time, that's, you know, good in its own way. But it's you know, getting in there and getting your hands dirty that really kind of like exposes what's going on and lets you get to know it at a deeper level. So this is all really good experience I'm hearing.
Yeah, I think having the issues and then drawing it out and going, wait, why isn't this working? And figuring out you're kind of getting a better understanding of how it all works and how you need to write it.
Definitely. And yeah, that's what you're going to be encountering a lot, right? Anytime that you're doing this kind of work with like new data structures, it's going to come down to being able to, you know, write some code and then test it and compare it to what you want to have happen. And that's often an exercise in drawing pictures and stepping through a debugger and comparing. So that's really good practice. That's good. And some of these data structures get pretty complex pretty quickly.
Yeah, I found this one to be easier to understand than the last one. I think that one, the hash was, to me, one of the weirder things, and then once you get it, you get it, you know. This one was actually a lot easier to write because we're using a lot of the same code. It's just the functions that are different. A lot of the main programming is very similar.
Okay, cool. Yeah, hashing is definitely its own kind of thing. Which, like I say, we're not going to be doing for the rest of the quarter, but you'll definitely use, you know, in other classes down the road. Let me see if I can find this. Here we go. So this was some code I was doing for Los Alamos actually a number of years ago. And this was the data structure that I came up with, right? It was something that pointed to a net list, which pointed to another net list, which was a linked list. But the first node of each of these linked lists was a pointer to another node and another linked list running vertically that pointed, so it was a list of lists, and each of these had, you know, various fields inside them and so on. And, you know, this was not like any structure I had ever, you know, studied or built before. And, you know, I made an ASCII art picture because I needed to refer to this so many times and go inside GDB and trace things around and see, you know, is this thing actually pointing to another sentinel node that's pointing down here and so on. So it's all really good practice, and it's definitely minutia. It's definitely, you know, super low level detail oriented stuff, which doesn't always work after like 12 hours of coding. But the more you work with this kind of stuff, the better you get. The more our brains seem to get wired for you know, staring at a bunch of hexadecimal numbers in GDB and saying, aha, you know, this should be a 3 instead of an E. And your friends just kind of look at you like you're crazy. All right. Any other PA4 questions, comments? Now I'm looking at some really badly written code. All right. So let's
Can we talk about the structure of the void LNRs, void NLRs, and void LRNs, please?
Sure. So tree traversal. So here's the pre-order. This is related to what I was about to talk about, so it's a good lead-in actually. This is the pre-order node left right. We take a root, which is a struct node star or an uppercase node, and your base case is, you know, if root is null, just return. So nothing to see. Otherwise, what do we do? Well, the pre-order part says the first thing we want to do is print out the root node's data. So print f root arrow data, which for us means, you know, a printf with some %s's, and we're going to print the plate, the first name, and the last name in whatever order the assignment specifies. But effectively, you know, we're printing the data portion of the root. So that takes care of the end piece, and then we want to print the left subtree. And how do we want to print it? Using node left right. So the next statement is just node left right, root arrow left. And then we want to print the right subtree, and again, how do we want to print it? Using node left right. So just call node left right on root arrow right. That's the end of your function. So it's exactly a 4-line function, a base case to see if the root's null, and if it is, just kick out. Otherwise, print the data that's at the root, and then traverse the left and right subtrees, and traverse them using node left right. Why are we doing node left right? Because we're trying to write the function called node left right. If you want to do in order, left node right, this would be void left node right, if the root's null return. But we would start off with left node right on the left subtree, and then print the root data, and then left node right on the right subtree. That's in order. If it's post order, it will be LRN if the root's null return. Otherwise, do LRN on the left, LRN on the right, and then print the root node data. Is that cool?
Cool.
Awesome. Yeah. So let's look at these traversal orders. We know that if you do in order, it prints out your data in order, smallest to largest, for the trees we've been talking with. So the first thing this will print will be the smallest node in the tree, and the last thing will be the largest node in the tree. Post order is interesting. We've already seen that if we have kind of a typical tree, and we do this in left-right node, well, left will bring us down to the 10, right will bring us to the 30, node will bring us to the 20, and then we'll go to the right, which will be a 50 and a 70 and a 60 and then a 40. So it's not clear that there's a significance to that ordering, because it's kind of oddball. Node left right. Let me do a different color here. Node left right would start here and print out the root node, so it'll print out a 40. And then it will traverse the left subtree. And to traverse that, first we'll print out the root node, and then the left, and then the right. And then we'll traverse the right subtree, which we'll do by printing out the root, and then the left, and then the right. So it starts off here, and then it goes down here, and then down here, and here, and then up here, and then down here, and then over there. Cool. And that's a weird order. So left-right node, the post order, just kind of like comes down here, and then goes there, and goes up here, and then it comes down here, and goes here, and does this one, and then it does the root of the tree at the very end. It turns out left-right node is a useful order for evaluating arithmetic expressions. And so here's an example. Suppose you wanted to evaluate A plus B times C plus D. So we want to do this addition first, and then this addition, and then multiply those two sums. And we know that normally, if we didn't put in parentheses, B times C would get done first, and then we'd add A and we'd add D, we'd get the wrong result. So we can describe this operation using a binary tree. And it won't be a binary search tree because there's no ordering involved here, but we can make a binary tree to represent this expression. So let's say we want to do, I'll do uppercase letters, A plus B times C plus D. And we can represent this with a tree as follows. I'm going to write A and B down here, and I'm going to make them children of an operator, which is a plus sign. And over here I'm going to put down C and D and make them children of an operator, which is a plus sign. And then I'm going to make those two plus signs children of the operator multiplication. And so this tree basically describes this expression. It says, okay, I want to do a multiplication. What do I want to multiply? I want to multiply this thing and that thing. Okay, what is this thing? This is B and A added together. That's that term right there. What is this thing? That's C and D added together. That's that term right there. And so this tree represents that arithmetic expression, including the parentheses, right? The fact that we want to do this, and then multiply the two results. And it can be tricky to evaluate that just by looking at the string and figuring out where you are and so on and so forth. But an easy way to evaluate that, if we turn it into a tree, right, which we can do pretty easily. Every time you find parentheses, that's going to be a subtree, right? If you turn this into a tree and then you do post-order traversal, you end up with something really interesting. So post-order says first go to the left. That's going to give us an A. And then go to the right will give us a B, and then do the root node, which is a plus. And then evaluate the subtree on the right, which will say go to the left, which is a C, go to the right, which is a D, and then do the plus. And then visit the root node, which is a star. So if we build a binary tree from this expression, and then we traverse it in post order, we end up with this interesting expression. Does anybody recognize this kind of expression?
Order of operations.
Can you say more on that?
It's a stack. You can put it in a stack, and you push them all in there, and you pop the stack, and you'll do them in order.
All right, cool. Anybody else seen something like this before? So this is something called postfix. And it's also called reverse Polish notation, or RPN. And it's a different way of describing an arithmetic expression.
So you're telling me people do math on a piece of paper like this, right?
No, but they used to do it on calculators.
Ah.
Right? So there was a line of calculators in the 60s, 70s, made by Hewlett-Packard. They were among the first pocket calculators, and they were the coolest machines out there, right? And they worked with reverse Polish notation. That was the way that you entered things in. And I'm looking at one on.
It's like how you would type out a number a little bit too, you know?
Yeah, yeah.
Operand, operation, I guess.
Mm-hmm. So yeah, this would have, among other things, it had an enter key. And so you would type in A, enter, B, enter, and then when you hit the plus sign, the display would show the sum of these two things. And then you'd say C, enter, D, enter, hit the plus sign, it would show the sum of these things. And then if you hit a star, it would show the product of the last two things that it showed. And these were like amazing machines. I should bid on this because it's only $25. These cost hundreds of dollars, you know, at the time. And I actually had, like, you know, a collage of HP calculators cut out from centerfolds of Scientific American. They would have a fold-out display in the middle with Hewlett-Packard's ad. And they were the calculators that everybody wanted to use. But the cool thing was, if you didn't know how to use an HP calculator and a friend tried to borrow yours, they didn't know how to use it. Because, you know, most calculators were built on arithmetic expression. You'd say parentheses A plus B close paren times parentheses C plus D close paren equals, right? And this one was different. But this turned out to be a really, really comfortable way to type expressions into a calculator. And once you got used to it, this was the way that seemed right. It seemed natural. And part of the reason why the calculators use this, because this expression is really easy to evaluate. And as someone said a few minutes ago, we can evaluate this kind of expression using a stack. And so a classic assignment is to build a stack-based calculator that will take an expression like this and give you the result.
When I took that assessment in Java, that was our first lab.
Awesome. It's fun to do, man. It's pretty cool when it actually works, and slightly magical to me, at least.
It seems like you could use this in a lot of different kinds of data structures, and more than just arithmetic. Like, let's say you have a series of operations you want to happen in some order, but you've got all this data to work with. You know, you could lay it out as you lay it out like this to get some result to run it, right?
Mm-hmm. Yeah, yeah. So how do we evaluate this with a stack? We have a little algorithm, which works like this. So read next token. If it's an operand, push it onto the stack. If it's an operator, pop, pop, operate, push result. And go back up and just keep looping. If there's no next token in your input, you're done. So you have to tokenize your input. Now I've made my variables single letters. I've made my operators single characters. So it's really easy to tokenize. But you know, if this was, you know, something with numbers or long variable names, you need to do something to know that, you know, this is not a variable called AB. It's a variable A, variable B. But we're just doing pseudocode here, right? So when I say read the next token, it's just these symbols, which could be, you know, big long numbers or something like that. So read a token. If it's an operand, a thing, you know, a noun, a thing you're going to operate on, push it onto the stack. If it's an operator, a verb that's going to do some action, pop the top two things off the stack, apply the operation, push the result back on the stack. and just keep doing that. And magically, this does your calculation for you. So let's make a picture of the stack. So here's our stack. And we're going to grow in that direction. So let's read the first character of our input. That's the letter A. That's an operand. We're going to push it. So we push an A on the stack. Go back to the top, read the next token. That's a B. That's also an operand. Push that on the stack. So now we got two things on the stack. Read the next token. That's a plus symbol. That is an operator. If it's an operator, pop the top two things from the stack. So pop off the B, pop off the A. Apply the operation. So do A plus B. Push the result on the stack. So now the only thing on our stack is A plus B. Go back to the top, read the next token, that's a C. It's an operand, push that on the stack. Read the next token, that's a D. It's an operand, push that on our stack. So our stack has three things on it now. It has A plus B, and then it has C, and then it has D. Go back to the top, read the next token, that's a plus sign, that's an operator. So what do? Pop the top two values from the stack. Pop off the D, pop off the C, apply the operation, and push the result. So now we push a C plus D on the stack. Our stack has two things on it now. Top of the stack is C plus D, next thing is A plus B. Go back to the top of our loop, read the next token, that's a multiplication. If it's an operand, no. If it's an operator, pop off the top of the stack, so that's a C plus D. Pop off the top of the stack again, that's an A plus B. Let me put some parentheses here. Apply the operation, which is multiplication, push that onto the stack. So now the thing that's pushed on the stack is, A plus B times C plus D. Go back to the top, read the next token. There's no token left, we're done. And our answer should be the one thing sitting on the top of the stack. So that's a nice application of a stack. And it comes from a stack basically because these parentheses are saying remember this. Right? We're going to do A plus B, and then we need to remember that. And we're going to do C plus D, and we're going to remember that. And then if we wanted to, divide this by, A minus B times C minus D plus E, right? Once we finish this calculation, we need to remember that somewhere so we can start doing this calculation. And then once we finish with that, we've got this and this, now we're going to divide them. So we're kind of using a stack-based structure, and these parentheses are basically saying, group this thing and stick it away somewhere. That's what the stack's doing for us. All right, other questions? All right, let me see, I got a question in chat here. When we delete a plate, we will search them first. So the search function will be called in the main file. A found called delete function, or it should be in the delete function. Good question. So if you look at the prompt for PA4, so the delete function doesn't have a way to tell us whether it succeeds or fails. Right? We can't return null for failure, because if we delete the root of a single noded tree, it should return null as the new root. And there's really nothing in this prototype that we can use to indicate whether the delete succeeded or failed. So if we leave it up to delete to search for the plate, at best it could simply return, silently the unchanged tree without making any modifications to it. But we definitely don't want the delete function to print something, right? That would be a really bad delete function. For example, if you wanted to free up memory by deleting every node in your tree, you wouldn't want to, have that printing messages and so on. So the fact that our main program should tell us if we try to delete something that's not found, right? Tells us that we should probably check for a node in the main program before we call delete. So in your main program, if the user says delete a node, go ahead and check with the search function to see if that node exists. If it doesn't exist, print a message from main. If it does exist, then go ahead and call your delete function. Does that make sense? And delete's a lot easier to deal with if you assume the node is in the tree anyway, because you never have to deal with a case where you're trying to delete from a null tree. Alright, so let's take a break. Let's come back at let's come back in about 5 minutes, and then I want to look at other ways to do tree traversal without using recursion. I want to look at tree traversal using a stack and a queue. So we'll come back to that after break, and that'll give us another application of stacks and queues. Alright, so I'll see you back in about 5 minutes. All right. Let's continue. So let's talk about traversing a tree without using recursion. And remember, unlike a list, when we traverse a tree, we hit these decision points where we have to say, should we go left or right? And whichever way we go, we need to remember that there's another way we still need to deal with. So, once you get down to, let's say we're doing in order, right? Once we've traversed all of this stuff and we get down to here, and we want to traverse this subtree, right? We need to somehow go down and hit all of these nodes before we come back and do this node and then the right subtree. And the deeper we go, the more stuff we need to remember, the more places we need to keep a marker to say, oh yeah, once I'm done, doing this subtree down here, I need to come back and do the node that I branched off of. So you need some kind of memory structure. And it turns out the way that this traversal order works, we're tending to go deep before we go across. Right, we're going to do everything on the left subtree before we ever visit this root node or do anything on the right. So we're going to go down, 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 down until we get to what will be the leftmost node in the whole tree. That'll be the first thing that we print. And then we're just going to pop up one level, print the root node, and then start going down to the right. And if there's other stuff hanging off of here, we're going to do all of that, all of that, all of that, until we come back and pop up one more level from this root and say, okay, let's do this node. And then we're going to go do everything on the right of that. And eventually, we're going to come back up and do this root node and then start going down on the right. So left node right, actually all of these traversal orders we've been doing are depth first. And depth first is a general term for how we can explore a search space. If it's a two-dimensional space, or something we can think of as two-dimensional, there's usually, a question of which direction do you want to make your primary search direction, and which one is secondary. So when you're running a maze, I'm going to do a really horrible drawing of a maze here. If you make a turn and you hit a dead end, do you back up to your previous decision point, or do you go all the way back to your first decision point to try something different? What you're doing is exploring a space of possible paths through a maze. And ultimately, unless you get lucky and find the way to the exit, ultimately you need to explore all the possible paths. But the order in which you do them depends on your algorithm. And so we can think of it as depth first or breadth first.
Am I the only one hearing some weird feedback?
I don't know.
No, I have no. I am. Me too.
Okay, just want to make sure.
What kind of feedback? Let me tweak my audio a little. Hold on. Testing 1 2. Testing 1 2 3. Bring that up. Let me do this. All right, testing 1 2 3. Alright, let me know if it stays weird. Well, okay, that's worrying. Let me know if you can hear me right now. So can you hear me?
That's a no, Nick.
Okay, Alright. Well. Alright, how about this one? This one's probably bad quality, but can you hear me on this? Nope. Alright, how about this one?
That works.
Okay.
Hear you now.
I'm guessing it's not as good quality?
Not quite, but
Workable? Alright, that's the microphone inside the document camera. I don't know why the other one would have gone away though. But
Yeah, we're just hearing some weird feedback. It's kind of weird.
Weird
Strange.
feedback, screeches, and thrumming.
oh wow. Okay. Maybe it's the squirrels outside, I don't know. Alright, let me go back to screen share. Alright, let me know if it gets weird again. Alright, so let's look at how we can do tree traversal kind of manually. So here's a behaved tree. And we're going to do in order, so left node, right. So here's the algorithm we use. First step, push the root. We're always going to push onto the stack, so push the root, onto the stack. But I won't keep saying onto the stack. So we seed the whole algorithm. We initialize it by pushing the root of the original tree onto the stack. And then we go into a loop. And the loop says move left and push the node that you're at. And repeat till there's nothing left to move on the left, till your left child is null. Alright, so first push the root on to the stack, and then start moving to the left. And at each node, push the node that you're at onto the stack and move to the left. Push the node onto the stack, move to the left. Keep doing that until you can't go left anymore. Alright, and then we're at a new section of the algorithm called L2. So L2 says pop the top of the stack, print it, and then if there's something to the right, so if right is not null, push right and go back to loop. Otherwise, go back to L2. So here's pseudocode with go-tos in it. Don't tell Scott.
go-to equals harmful.
Yes. So let's put our tree up here. And let's traverse this tree using this algorithm. So I'll make a stack here. and we'll grow the stack in that direction. So this will be the bottom of the stack. Alright, so what do? We push the root onto the stack, so we're going to put a 40 on here. And then we're going to start moving to the left. So we'll come down here, we'll push the 20 onto the stack. We'll go back up to loop. We'll move to the left, there's a 10, we'll push that on the stack. Repeat until you can't go to the left anymore. So we're done with the loop part, and now we come down to L2. And L2 says pop the top of the stack and print it out. So we're going to print a 10. Let me put my output here. So we're going to print the 10 that we just popped. And then if there's something to the right, we're going to push that. So we'll push the 30, and we'll go back to L2. Sorry, we'll go back to loop. So loop says move left. Well, there's nothing to the left of 30, so we can't do that. So we'll come back here. We'll pop the top of the stack and print it. And then if there's something to the right, we would push it. Well, there's nothing to the right of the 30, so we go back to L2. So L2 says pop the top of the stack, which is a 20. Oh, I messed up, man. Alright. Let's try that again. Push the root. Move left, push that. Move left, push the 10. Can't move left anymore, so pop the top of the stack. So that's our 10. And print it. And then if the right is not null, we would go back to loop. But the right of the 10 is null. Right, so we're going to go back to L2, and L2 says pop the top of the stack, which is a 20, print it. And if there's something to the right, which there is, we're going to push that, so we'll push our 30, and then we go back to loop. So from the 30 we try to go left, we can't, so we're going to come here, we're going to pop the top of the stack, which pops off the 30. We're going to print it. And now if there's something to the right, we would go down there. Well, there's nothing to the right of 30, so we're going to go back to L2. We're going to pop the top of the stack, which is a 40. And now if there's something to the right, which there is, we're going to push that onto the stack. So we'll push a 60 onto the stack, go back to the loop. So from the 60, we're going to move left, which means we'll push a 50. We can't move left any further, we go to L2. L2 says pop the top of the stack and print it. So there's our 50. And if there's something to the right, push it. Well, there's nothing to the right, so we're just going to go back to L2, pop the top of the stack, which is a 60. And if there's something to the right of 60, which there is, we will push that onto the stack. So we push a 70, and we go to loop. Loop tries to move left, we can't, and so we're going to come down to L2, pop the top of the stack, which is a 70. Print it. There's nothing to the right, so we're going to go back to the top of the loop. We'll try to move left, there's nowhere to move. We try to pop the stack is empty, we're done. And so there's your in order traversal. Why does this work? It's a little hard to see. But if you go through the spirit of it, right, this is moving as far left as possible. That's what loop is doing. When you can't go any further left, the leftmost thing, the last thing you push down the stack, that's the number you should print next. So we pop that off and print it. And then if there's stuff to the right of this, right, this is the node part. If there's stuff to the right, we need to traverse that next. That's the R part after the node. If there's not, then we go back here. Popping basically moves us up one level. So we'll go up one level, and then we'll immediately start trying to go down to the right. And if we can go to the right, we'll push this node on, and then begin the whole, left node, right traversal of this subtree. But this is, certainly more complex to understand. It's pretty straightforward to code if you have a stack. But it's certainly not as kind of neat and clean as you know, just the recursive left node right. Right, so something like this, where we just print and then we call the same function to traverse the subtrees. But nonetheless, this gets you the same result. Alright, and someone says that helps understand how LNR works, which is cool. It's worth spending a little bit of time practicing tree traversals on paper and just kind of trying to get a feel. Don't go with something, you know, really super crazy. But you know, something like this, left node right, so go left, go left, go left, that's going to be the first thing you print out, is a 10. And then hop up one level to do the root, that's a 20. And then come down to the right, but don't just print this right node, go back and repeat the whole process. So from here, go left, 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 as far left as you can, print that out, pop up one level, and then come down to the right. But don't just print that root node, begin the whole recursive thing on this tree. So go left, left, left as far as you can, that's 26, and then pop up to the root, that's 27, nothing to the right. And now that you've finished that, you've done the whole traversal of this left subtree, now pop up one level from where you started, pick up the 30. Now that you've done that, you've done the whole traversal of the tree rooted right here, pop up one level from that, do the 40, and now go in and do the right subtree. So that's the spirit of these depth first traversals. So any questions about that? Awesome, you're welcome. Alright, so what happens if we do the same thing but we use a queue? So here's a queue-based traversal algorithm. So we need to seed the algorithm. Most of these algorithms you have to start it off somehow. So in this case, we've got a queue. We can insert at the tail, we can remove from the head. So so let's insert the root. And I'll just put a note here. We're inserting at the tail of the queue. And then we begin a single loop. So we remove whatever's at the head of the queue. Let's call it N for the node that we removed. Print that node's data, and then insert that node's left child and that node's right child, if they're not null. If there's no left child to N, don't insert null into the queue. Just don't do anything. If there's a right child, insert the right child. And iterate over that. And if the queue is empty, then you're done. So this is a simpler looking algorithm, right? It's a single loop. And there's really not a whole lot of conditionals in here. Start off by putting the root into the queue, and then just remove the head of the queue, print it, insert its two children into the queue. And just keep doing that until the queue is empty, and then you're done. So let's see what this does. We'll do a slightly more interesting tree. So this is a binary search tree. We're going to print it using this queue-based traversal algorithm. So let me make a picture of my queue down here. And I'm going to imagine that the head of the queue is over here on the right, so the direction of stuff flowing through the queue is basically from left to right. But, you know, I'm just going to write things and scribble them out and write other things and so on. Alright, now record the output. Here. So we see the algorithm by inserting the root. So 40 is the first thing that goes in. So that's sitting at the head of the queue. Alright, so step 1, remove the head of the queue. So we remove the 40 from the queue. That's n. We print out n's data. So that's a 40. And then we insert n left into the queue. That's a 20. And then insert n right. That's a 60. So, you know, we wouldn't be inserting an integer. We'd be inserting the address of a struct node or whatever these structures are called. We're actually putting, you know, a pointer to that node in. But I'm just writing down the data values as a way to identify what node we're putting into the queue. But it's actually a queue of, you know, struct node stars or something. Alright, so we inserted the left and the right subchildren of that 40. We go back up to the top. So remove the head of the queue, which is a 20. Print out that thing's data. So we'll print out a 20. This is removed from the queue. And now we insert the left and right children of 20. So we insert a 10 and we insert a 30. Make that a little bigger. Alright, go back to the top, remove the head of the queue, that's a 60. Print its data, so that prints a 60, and then insert the left and right children. Well, the left child is a 50, and the right child is a 70. Go back up to the top, remove the head of the queue, that's a 10. Print its data, and then insert the left and right children if they're not null. Well, both children are null, so there's nothing to insert. Go back to the top, remove the head of the queue is a 30. Print its data, insert the left and right children, there's no children, so nothing to do. Go back to the top, remove the head of the queue is a 50. Print its data, insert the left child, which is 45. Right child is null, nothing to insert. Back to the top of the queue. Remove the head of the queue is a 70, print its data. Look at the left and right children, they're both null, nothing to insert. Back to the top of the loop. Remove the head of the queue is a 45. Print that, insert the left and right children, they're both null, nothing to insert. Back to the top of the loop, remove the head of the queue, guess what, the queue is empty, we're done, and that's the output that was produced. So how can we interpret the order of this output data relative to the tree?
Would this be a pre-node traversals, like node and then right and then left? So NRL?
That's possible. So the 40 came out first, that's the node. And then if we go left, we printed that node. But then we jump up and we go to the right of the original node.
Oh, that's a 20, not a 70. Oops.
Yeah.
Oops.
So anyone see what the order is related to?
Oh, it's a breadth first.
Mm-hmm.
Gotcha.
So depth means going down, breadth means going across. And so if we start with the root, right, there's a 40, and then we come down one level, right, this is a node with depth 0, go down to a depth of 1, and instead of going any deeper, print out every node at that depth. There's a 20, there's a 60. Now that we've done all the nodes at that depth, go down one level deeper, that's right here, and just print these out from left to right. There's a 10, a 30, a 50, and a 70. And now we're done with the nodes at that depth, go down one level deeper, and print out the 45, and that's every node in the tree. So very different traversal order. It's not sorted numerically. It's sorted in some sense sort of visually or graphically. From top to bottom, printing out each level from left to right. And this is this two-direction of traversal thing that I was alluding to earlier. We can think of this as kind of a two-dimensional space of data. And one option is to, sort of come down first and move in this direction more quickly than we move in this direction. With an in-order traversal, we're going to do everything over here before we ever come to anything to the right of the root. A breadth first is really the opposite. We're going across and doing everything at this level before we go down. We're moving more quickly in this direction. This is perhaps a more useful way to traverse if you wanted to print a tree. Printing a tree is a really interesting challenge because you don't know, even when I draw it on paper, I mess up and I put my stuff too close to each other, right? But if you wanted to try to print a tree from inside code, you would probably want to do this kind of traversal order because we're going to want to print these nodes before we print these and print these before we print these. Because, when you print, you're usually printing from top to bottom on a piece of paper or a screen. This is also a really useful way to try to get a better idea of what a tree looks like. And, we don't know if this 45 is sitting here or here or here or here, but we know it's sitting a level below the 10, 30, 50, 70. And so a queue-based traversal can be kind of at least a good sanity check on tree manipulations. If I print this out and the 45 comes out, on the same level as the 20 and the 60, I know I got something that looks different from this. And so that can be a nice use for this. And stacks and queues work like this. They sort of satisfy two kind of fundamental different approaches to algorithms. This idea of depth versus breadth pops up a lot. And it's probably not entirely unrelated to like array ordering. So like if you have a two-dimensional array of data, I'm just drawing circles now so I can't stop. Alright. So you have a two-dimensional array of data, so int data bracket 6 bracket 6. You know that in the memory of the computer everything is one-dimensional, right? If you have 16 gigabytes of memory, you have 16 billion bytes stored one after another. And it's just a sequential one-dimensional array, basically. But we can represent things with higher dimensions, like two-dimensional data. And so typically, you know, this would be element 0, 0. But what would this element be? Would it be 0, 1 or 1, 0? It really kind of, you know, it's more or less random. So in most languages today, this would probably be 0, 1, 0, 2, all the way over to 0, 5. And then this element would be 1, 0, over to 1, 5. This would be 5, 0, and this would be 5, 5. But that's just one possibility. The other possibility would be like this. Is one better than the other, or more correct, or more natural? Not really. It's more or less completely arbitrary. But what these represent are two different ways of moving through a two-dimensional space. So we could, you know, sweep through this data like this, move across these, and then come down and move across the second row, come down, move across the third, and so on. And that might be the order in which these things are stored in memory. Or it could be that these are stored with, you know, the first 6 things in memory are sitting in this column, followed by these 6 things, and these 6, down to that. And it varies from language to language. So this is called row major. This is called column major. And it's kind of like, you know, a breadth first versus a depth first. You need to move across and you need to move down to get to the different elements in this matrix of data. If you go through the data in order, which way are you moving first? Are you moving across or are you moving down? It's kind of the same idea of two types of traversals. So if we code this up with a queue, we're definitely doing breadth first. If we coded with a stack, we're doing depth first. If we coded recursively, we're also doing depth first. Because recursion is stack-based. When we have a function and we call ourselves, we take our local variables, we take our return address, and what do we do with them? We put them on a stack. And we're not going to come back to those values until all the subsequent calls that we've made after that have returned. So it's this fundamental, you know, first in, last out structure. That's why recursion is stack-based. All right, questions about that? That's more kind of like conceptual than anything there. Let's start talking about dynamic programming. So this will lead into PA5, and we're kind of leaving the subject of trees per se for a while, but we're still talking about trees, but we're kind of focusing on a different aspect of computation than the trees themselves. And let's think about recursion and recursive functions, and let's go to our favorite recursive function, which is Fibonacci series. So this is in harmony with where we are in 215. Fibonacci series are defined by a recurrence relation which says the first two terms of the series are 1, and the nth term is the sum of the two previous terms. So fn minus 1 plus fn minus 2. And so if we want to write down the terms of this series, right, f0 is a 1, f1 is a 1, f2 will be f1 plus f0. Well, that's 1 plus 1 is 2. And then f3 will be f2 plus f1. Well, that's a 2 and a 1. That's 3. And then f4 will be f3 plus f2. That's a 3 and a 2 is a 5. f5 will be f4 plus f3. That's a 5 and a 3 is 8, and so on. And so we just keep adding the two previous terms, or the last two terms of the series, to get the next term. And we get this fun series of integers. And it's like one of the coolest series in our part of the universe. And it pops up in nature, it pops up in music and in art and all kinds of things. It's a beautiful series. If you've never studied it or looked at it, definitely do some Googling. And this was discovered, I think, almost like 1,000 years ago, something crazy, like 1400s or something. And it was studied by analyzing theoretical growth of a rabbit population. And I have a really cool textbook that talks about Fibonacci and what he was doing at the time. And this was an example in a book that he wrote. And nobody remembers the book, but this one example just became famous. And it's seriously one of the coolest series that you could encounter. And it's so simple, right? It's just, each term is the sum of the two previous terms. But it pops up all over computer science and all kinds of stuff. All right, so once you learn about the series, what do you want to do? You want to go off and write a program to generate Fibonacci numbers, or at least that's what I did. And so, it's not a very complex thing. You can keep track of the last two numbers and just keep adding them together, and there you go. So let's
I think we did this in Python for 101, and we just used like a for loop.
Oh, cool, awesome.
We just did like I and J.
Nice. So here's a way to generate Fibonacci numbers, right? Start off with my last term is 1, and last 2, which is, the previous term is also a 1. And here's my do forever loop. And I set this number equal to the sum of the last two numbers. And I'll print that out, and, I'll keep track of, the nth Fibonacci number. So I'll print fib, parentheses, whatever I'm up to, equals, and I'll print out that number. And then I just, adjust the last two numbers I'm remembering. The last number I'm going to remember is the one I just printed, and the number 2 spots back that I'm going to remember is what I was calling the last number. And so I'm kind of like when you do current previous going through a linked list, I'm just keeping track of the last two calculations. And so if I run this, we get tons of Fibonacci numbers. But let's look at the ones in the beginning, right? So there's 2, 3, 5, 8, 13, 21, 34, 55. Miraculously, I predicted those through pure coincidence, right? So this works great. And, I'm printing it as a long integer, so I can get above 2 billion, but I'll overflow the bounds of a 64-bit integer pretty quickly, and suddenly my numbers will go negative. Looks like right about here. But I can get up through the 90th Fibonacci number pretty easily. And even though the numbers, aren't correct, they're being rounded modulo 2 to the 64th, right? It takes no time to calculate these. I mean, to calculate each number, I just have to add two numbers together. And, the only thing slowing this down is the print statement. If I wasn't doing that, right, I'd be cranking tons of these things out. But, we're already up to the 3 millionth Fibonacci number here. So that's a pretty simple thing to code. But it turns out that if we use this original notion of what a Fibonacci number is, we could say, hey, I know about recursion now, let's write a recursive function for this. And so wrong window. So let's do that. So I'm going to write a Fibonacci function called fib, takes an n, returns an integer, and I'm going to try to print out the first 1,000 Fibonacci numbers. So I'm just going to call fib n and save the result as answer, print that out as a long integer. And my fib function is trivial. If my number is less than or equal to 2, I'm going to return 1. Otherwise, I'm going to return fib of n minus 1 plus fib of n minus 2. So this is a direct interpretation of this description of a Fibonacci function. And it will do the right thing, but it'll do it very slowly. Now, we can go back and we can see it printed out the right numbers in the beginning. There's our 89, 144, and so on. But it gets really slow. And there's no reason for this, right? The 46th Fibonacci number is just the sum of these two. And, it's going to end with a 3 and then a 0 and so on. And if I add these two numbers together, I'll get the 47th. And I could probably do that before the computer is going to figure out what it is. It's going to be something 073 at the end. And it'll get there eventually, but it's going to take a really long time. There we go. And so this is just slowing down really fast, and it's never going to make it to the 90th Fibonacci number. It's going to take way too long. But the function is really simple, right? It's just, return fib n minus 1 plus fib n minus 2. So why is it taking so long? It's got to be that this function is getting called a bunch of times. So here's a modified version where I use a global to keep track of how many times I call the Fibonacci function. And so I initialize a count to 0 before I call fib n. So I'm going to generate 1,000 Fibonacci numbers. Before each one, I'm going to zero out this counter. And then inside my Fibonacci function, right, if my number is less than or equal to 2, I just return 1. Otherwise, I'm going to make a recursive call to my Fibonacci function. I'm going to bump up my count first and say, hey, I'm doing some recursion. So count tells me how many times I did this recursive statement. And then I'll return the Fibonacci function. So when I'm in my main program, after I've calculated the nth Fibonacci number, saved it as answer, I'm going to print that out, but I'm also going to say the fib function was called this many times, and I'm going to print out the value of count. So if I do that, right, it's still really slow. But take a look at how many times my function's being called. 1, 2, 4, 7, 12, 20, 33, 54, 88, 143. To calculate the nth Fibonacci number, I end up calling my Fibonacci function about as many times as the nth Fibonacci number. If I count the initial call to fib as 1, it'll actually be exactly the same time. So it's not that, adding this number and this number together to get 610 is that hard. It's that to calculate the 610, I have to call my function recursively 609, 610 times. So yeah, it's like order of fib n minus 1. And the nature of these Fibonacci numbers, you know, they more or less kind of double each time, right? If you keep adding two things together to get a new thing, it's somewhere on the order of, you know, doubling or 1.5 or something like that, which means the amount of work I'm doing to calculate the next number is increasing by this geometric amount. And so, you know, I could actually calculate the Fibonacci number by timing how long it takes to calculate the next Fibonacci number and turning that time into a number, which is kind of weird. So this is taking forever. So why is this function so slow? Yeah, this is like Towers of Hanoi, which we also do in 215. So what's going on here? And we can study the behavior of this by using a tree. So I'll usually just call this a call tree, but we can also think of it as a recursion tree. And here's what's going on. Let's say we want to calculate the 8th Fibonacci number. Alright, so f of 8. Well, to do that, we need to do two things. We need to calculate f of 7 and f of 6. Alright, how do we calculate f of 7? We need to calculate f of 6 and f of 5. How do we calculate f of 6? We do f of 5 and f of 4. And how do we do f of 5? We do f of 4, f of 3. And how do we do f of 4? F of 3 and f of 2. And how do we do f of 3? We do f of 2 and f of 1. And I don't want to write any more, so I'm just going to assume that these are our base cases, and that these can be calculated without making recursive calls. But this f of 3 up here, we have to do f of 2 and f of 1. And this f of 4, we have to do f of 3 and f of 2. And this f of 3, we have to do f of 2 and f of 1. And these are base cases, so there's no recursion. And this f of 5, we have to do f of 4 and f of 3, and so on. Alright, so just look at it up to here, f of 6, right? We had to do all of these calculations. And now to do f of 7, right, we're going to have to do all of this work plus f of 5, which is all of this work. So the amount of work involved to do f of 7 is the amount of work for f of 6 plus the amount of work for f of 5. That's the Fibonacci relationship. That's why the number of function calls is, you know, the Fibonacci series. And as a consequence, you know, we're going to have to do all of this work just to find f of 7. And then when we're done with that, we're going to have to do f of 6. And f of 6 is going to look like this whole tree over here. So we're going to have, you know, all of this stuff that we're going to do just like we did over here. And it's a huge amount of work. Alright, so what do we do about that? We make the following observation. When we're trying to calculate f of 7, we have to do f of 6 and f of 5. Well, let's say we do f of 6 first. We've got to do all of these calculations down here. Along the way of calculating f of 6, guess what? We're going to calculate f of 5. We're going to do all of this recursion and come up with a value for f of 5. When we try to do f7, right, we've done f6, we're going to have to do f5 again. Why should we repeat all of this work to find f5 when we've already done it once before? So when we calculated f6, we found f of 5 and f of 4. And so now when we're calculating f7, right, we need to calculate f of 5. Let's not go through all of that recursion again. Let's remember the value that we found here and just use that. So this is like a cache memory. when we calculate the value of this function for some argument, we're going to remember what that value was. And we're only going to do the hard work of calculating it once. And if we ever need f5 again, we're just going to use the value that we saved. And so over here, when we're calculating f of 8, right, we've just found f of 7. Now we have to find f of 6. Instead of doing all of these recursive calls over here, and there's going to be a huge number of those, we're going to remember when we found f of 6 previously, what the value of that was. We're going to save that in memory. And now when we say, let's find f of 6, we're going to say, oh, wait a minute, I remember that. I already calculated that. I know what that number was. We're just going to pull it out of an array that we used to save it. And so this is also called tree pruning. And the idea is, this whole chunk of the tree, we're just going to remove it. So we're not going to do any of these calculations. And this F5 part, we're just going to prune that off also. We're not going to do any of that. My pruner's not working very well. There's some good pruning. We'll prune that off. And if we've already calculated F4 here, we're not going to calculate this. And we're not going to have to calculate F of 6 again. And in fact, if we've already done F of 3, we're not going to have to do that F of 3 calculation. And so this is called dynamic programming. And the basic idea is, as we calculate results to our recursive function, we're going to save them in memory.
So you say a general strategy employed by all dynamic programming?
Basically, yeah. So let's adjust our Fibonacci function. We're still trying to do fib.52. Say again?
With the prime numbers calculator once. I've tried to do this with the prime numbers calculator once.
Oh, interesting. Did it work?
Kind of. I wasn't so good at using that, working with file IO at the time.
So yeah, you could use this for prime numbers because, you know, to test a number, you don't need to divide by every odd number below its square root. You only need to divide by prime numbers below its square root. And so if you can save your primes, you can get away with a lot less testing. Because if you're testing, you know, a number around 1 million to see if it's prime, well, there's 500,000 odd numbers. There's a lot fewer prime numbers. And so you can save yourself some time. All right, so let me spare this thing of its poor effort. I'm curious how much CPU time we're using. So yeah, that's chewing up 100% of the CPU, calculating Fibonacci numbers. Fortunately, I got 4 cores. All right, so let's modify this and let's add a cache. So here's the prototype for my fib function. Here's an array called array to save fibs. I'm making it 1 million. I don't need it to be 1 million because I'm not going to go that large, but you know, just in case. So here's an array where I'm going to save the results of calculating my Fibonacci function. And my main program is the same thing. I'm just going to go from 1 to 1,000, call fib n, print out the answer. And my Fibonacci function is almost the same as it was before. Right? So before it looked like this. If n is less than or equal to 2, return 1. Otherwise, return fib n minus 1 plus n minus 2. Now it's slightly different. So still, if n is less than or equal to 2, return 1. Otherwise, here's fib n minus 1 plus n minus 2. Save that in f and return it. But I got 2 extra statements here. And anytime we're doing dynamic programming, we're basically going to add these 2 statements in some form near the beginning and near the end of our recursive function. So in the beginning, right, I'm initializing my Fibonacci array to all zeros. That's a convenient thing to be able to do because my Fibonacci numbers are always positive. So 0 is never, you know, a valid Fibonacci number. And so by initializing my array of answers to all zeros, I know whether I have an actual answer stored. So in the beginning of my function, I'm just going to check the nth element of my save array, my cache. And if it's positive, I must have stored an answer in there. And the answer in the nth element will be the nth Fibonacci number. And so I'm just going to return the value stored in that position in the array. I'm not going to do any recursion in that case. So that's the case where I'm calling fib with a value of n equals 6. I'm going to look and say, you know, is there a positive number stored in the 6th element of my array? And if there is, it must be a value that I already saved, a calculated value for the 6th Fibonacci number, and I'm just going to return it. But if the value stored in there is 0, it means I've never calculated fib of n, in which case, well, you know, I'll just do my recursive calculation. Take fib n minus 1, n minus 2, add them together into f. But before I return, guess what? I'm going to save that calculation into my array. So that in the future, if I call my fib function with the same value of n, when I do this check, I'll see something bigger than 0. I'll see the number f, and I'll return that. Does that make sense, the basic setup? Because it's really no more complicated than that, but that can take some grappling with to make sense of.
Makes sense to me.
I think it'll just take some working with it to really sink in, but so far it looks alright.
Okay. Alright, so let's try this. Don't worry about the warning messages. Right, so there's the first 1,000 Fibonacci numbers. And, you know, we overflowed pretty quickly. But, you know, it definitely works until we get up to 2 billion. And so this has the advantage of, you know, being really easy to write. I don't have to keep track of multiple variables. I'm using the recursive definition of a Fibonacci function. But I'm also doing this caching of values so that I'm not calling myself, you know, a billion times to find these numbers. I'm saving the results along the way. I think I had trouble initializing the unsigned long. I didn't know about 0L or something at the time. But yeah, we could make this long unsigned and get larger values. But it still overflows pretty quickly. So this is called dynamic programming, and it's really just, you know, caching results along the way. And so one thing you see associated with this is the term repeated subproblems, right? The idea is we're finding the solution to a problem by breaking it into the solutions of simpler problems and putting those solutions together. That's the essence of when we think recursion, right? How do we find the height of a tree? Well, find the height of the 2 subtrees and then do a simple calculation. So we have a task we're trying to do. We break it into doing simpler tasks and taking the results of those and putting them together. That's the recursive structure. So that's one ingredient for when we want dynamic programming. The other ingredient is this repeated subproblem. The fact that you know, to calculate the nth Fibonacci, well, we calculate some smaller Fibonacci numbers, but in the process of doing that, we're going to calculate, you know, say f of 4 a bunch of times. And that's the part that we can use dynamic programming to increase the efficiency. So recursive structure and then repeated subproblems. So we're going to look at a number of kind of classic problems that lend themselves to these recursive solutions, but that typically have horrible performance. because of this repeated subproblem characteristic. Far worse than what we're seeing with Fibonacci, and we'll see how we can use dynamic programming to speed those up. So yeah, divide and conquer is really the recursive part, right? Breaking things into subproblems, putting them together, and you know that's what high-low is. Pick a number from 0 to 100 and try to guess it. Well, I'm going to change it into a problem of guessing a number between 51 and 100, right? And how am I going to do that? Well, I can turn it into a problem of guessing a number between 51 and 74, right? So I keep coming up with simpler subproblems. And when you have this kind of divide and conquer algorithm, right, you can usually express some kind of call tree that will describe how the big problem gets solved by smaller problems. All right. Other questions, comments about that? All right, so we're one topic ahead of the Monday-Wednesday class, and we'll talk about this in there tomorrow and then build on it. So I'm going to leave this here for now. I'll let you out 4 minutes early, and then on Thursday we'll take PA4 questions and so on as usual, but then I want to start digging into some of the problems that we can tackle using dynamic programming and see how this recursive structure and repeated subproblems pops up in different contexts. So we're playing with some really fun problems, dropping eggs off buildings, cutting up rods, winning shopping sprees at stores and things like that. So so we'll go ahead and we'll start with that on Thursday. Come by office hours if you want to go over code for PA4. Otherwise, I will see you next time. Thank you.
Thank you.
Thank you a lot.
Great day.
You too.
Have a good day.